All right, wizards. Same question again, but this time from a hypothesis test approach. So again, in a hypothesis test, we're going to place all of our faith and trust in the population proportion, what we believe to be true. So checking the conditions for big enough, since we're going to place our faith and trust in P, the population proportion, I'm using that to predict what I would expect to see in a sample of 200. So in a sample of 200, I would expect to see 146 identify as being very well off financially and 54 not. And since both of those are greater than 10, my sample is large enough to use a normal model. I'm not going to check this simple random sample because it says so up there in the top, and I'm going to assume that the 200 students is less than 10% of all students. So the null hypothesis. P is 0.73, which means the proportion of first-year college students identifying as being very well off financially as an important goal is a 0.73. Something to include, the evidence against the null hypothesis is what I collected in my sample. So my sample size was 200. There were 132 of the students who actually identified as being very well off financially as an important personal goal. And that makes for a p hat of 0.66. So 132 divided by 200 is 0.66. So that's my evidence against the null hypothesis. The alternate, it just wants to know, is it different from 0.73? So this is a two-tailed test. So my alternate hypothesis is P is not equal to 0.73, or that the proportion is actually different from 0.73. So write out the normal model we are using. So again, this is the population proportion, or our null proportion. That's the null proportion, and that's the null Q proportion. So I'm putting all of my faith and trust. I'm putting all of my faith and trust in this model, and I happen to see a p hat that was 0.66. So I'm curious to know is how likely would it be to have a sample in that tail, or, since it's a two-tailed test, to have a p hat in the symmetric tail. And so this is a two-tailed test. And my p-value is, again, I found the area that was in one of my tails. So here is 0.73, and here is 0.66. So I found the area that was in this tail. That's 0.01288, and I doubled that. I doubled that to get the two-tailed test. So that is 0.02576. That's why I multiplied by 2 there. So my decision in proper context, with a p-value of 0.026, I would reject the null hypothesis at the 5% significance level, but pay attention, I would fail to reject it at the 1% significance level. So the alpha level does matter. But at the 5% level, I have evidence. I have evidence to suggest that the proportion of first-year college students who identify as being very well off financially is an important personal goal is different from 0.73. So what does the p-value mean in context? Very similar to a confidence interval. If I repeatedly took, if I repeatedly took samples of size 200 from the same population, that is, where 73% of the first-year college students responding to a national survey identified being very well off financially as an important personal goal, I would expect to see samples with a p-hat of 0.66 or more extreme in either direction, about 2.6% of the time. So that's what that p-value means. It's kind of like, again, repeatedly doing this procedure. Can I conclude that the proportion of all first-year students at the university who think being very well off is important differs from the national value? Well, my evidence suggests it, but I can never really say with absolute certainty. At the 5% alpha level, I could say yes, but at the 1% alpha level, I would say no. So it depends on your alpha level. Describe a type 1 error in context. That's believing that the proportion of first-year college students responding to a national survey identified as being very well off financially as an important personal goal differs from 0.73 when in fact it's not different from 0.73. The type 2 error is believing that the proportion of first-year college students, I'm going to take out that responding to the national survey in both those. That the people believing that the proportion of first-year college students who identify as being very well off financially as an important personal goal is not different from 0.73 when actually it is. So this is where you reject HO up here, and this is where you do not reject. You do not reject HO there. The power of the test is the next question, I think. The power of the test, the ability to correctly detect when the proportion of first-year college students who identify being very well off financially as an important personal goal is different from 0.73 when it really is different from 0.73. So that's being able to detect when the alternate hypothesis is happening, when it actually is true. And then how could you increase the power of the test? Well, I could take a larger sample size, or I could use a larger alpha level. So that's the hypothesis test, kids. Hope that's helpful.